The morning of April 23rd, 1943, somewhere in the hills above Salerno, Italy, Lieutenant James Corrigan pressed his back against a stone wall that had been standing since before Columbus sailed, now pockmarked with German machine gun fire. His radio man, Private Eddie Walsh, crouched beside him with 38 pounds of equipment strapped to his back, the new SCR 300 radio that Signal Corps had promised would change everything. Walsh's hands were shaking, but not from fear. He'd been in combat before. What made his fingers tremble as he turned the radio's tuning knob was something different: disbelief at what he was hearing. Through the handset, crystal clear despite the German artillery falling 200 yards behind them, came the voice of Captain Morrison at Battalion Fire Direction Center. Station 3. This is fire direction. We copy your grid coordinates. Stand by for fire mission. 3 miles of Italian hillside separated Corrigan from Morrison. 3 miles of stone walls, olive groves, and enemy territory. By every rule Walsh had learned in radio school, that signal should have been crackling static, if it existed at all. The old SCR 194 radios would have been useless at this range, especially with all the interference from the barrage. But the voice in Walsh's headset was so clear Morrison might have been standing next to them. "Jesus, Lieutenant," Walsh whispered. "This thing actually works." Corrigan didn't answer. He was watching a German observation post on the ridge ahead, calculating distances, angles of fire. When he finally spoke, his voice carried the weight of a realization that was reshaping warfare even as it happened. "Walsh, we can see them. And now we can kill them from 3 miles away." If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Walsh and Corrigan didn't fully understand that morning, what most soldiers carrying the new radios didn't yet grasp, was that they were holding the culmination of one engineer's refusal to accept what everyone said was impossible. The story of how infantry could call fire from artillery batteries 15 miles away began not on an Italian hillside, but in a hotel room in Kentucky, 18 months earlier, with a man who believed that the entire military establishment was wrong about radio. To understand why Daniel Noble's frequency modulation radio changed warfare, you first have to understand the communication nightmare that American forces faced in 1942. The United States entered World War II with a military communication system that would have been recognizable to officers from the First World War. Artillery coordination relied primarily on telephone wire, thousands of yards of cable strung across battlefields, connecting forward observers to fire direction centers to gun batteries. When the system worked, it worked beautifully. Fire missions could be transmitted with precision. Multiple batteries could coordinate their fires. Artillery could respond to infantry needs within minutes, but the system almost never worked as designed. In North Africa, during the Kasserine Pass disaster of February 1943, American units discovered that German artillery had an unsettling ability to cut American communication lines at exactly the moment attacks began. Forward observers would set up their observation posts, string telephone wire back to command posts, register their reference points, and prepare to support advancing infantry. Then German shells would start falling, the telephone lines would go dead, and suddenly the most powerful artillery force in the American army couldn't talk to its own guns. The statistics were grimmer than most soldiers realized. Signal Corps studies showed that in mobile warfare, 70% of wire cuts came from friendly forces, tanks driving over, cables, trucks snagging lines, infantry stepping on connections. The remaining 30% came from enemy fire, but those cuts happened at the worst possible moments. A German artillery barrage that lasted 5 minutes could sever a dozen communication lines. By the time repair crews found and fixed the breaks, the tactical situation had changed completely. Wire communication had another fatal weakness. It was slow to establish. Laying 3 miles of telephone cable required hours of work by trained signalmen. In fast-moving combat, forward observers often couldn't keep pace with advancing infantry. The alternative, sending runners to carry fire mission information back to artillery positions, was even slower and far more dangerous. Runners were easy targets. Many never completed their missions. The UTMSS Army had portable radios, but these were almost worse than having nothing. The SCR-194 and SCR-195 amplitude modulation radios, developed in the mid-30s, operated in the 27 to 65 MHz range. They were temperamental devices that required constant tuning adjustments. Their effective range in field conditions rarely exceeded 2 miles. Any nearby vehicle engine, tanks, trucks, even motorcycles turned the radios into boxes that produced static and intermittent bursts of garbled speech. Artillery forward observers, using the SCR-194, reported a consistent pattern. The radio would work adequately during the approach march, when it wasn't needed. The moment combat began when every engine was running, when atmospheric conditions shifted from explosion shock waves, when the observer most desperately needed to communicate, the radio became useless. The smaller SCR-536 handy-talkie, introduced just before Pearl Harbor, offered portability but sacrificed range. Its effective communication distance was roughly 1 mile in open terrain, perhaps a quarter-mile in forests or hills. Useful for squad leaders coordinating with their platoons, but utterly inadequate for calling artillery fire from batteries positioned 8 to 12 miles behind the front lines. British forces faced similar problems with their own equipment. The wireless set, number 38, their standard infantry radio, had an effective range of about 1 mile. Even the more powerful wireless set, number 19, mounted in tanks, struggled to maintain clear communications beyond 3 or 4 miles in combat conditions. German forces, despite their reputation for technical excellence, weren't much better off. Their torn Fu-2 backpack radio could reach 10 kilometers using continuous wave Morse code, but only 4 kilometers with voice transmission, and it used amplitude modulation with all its attendant interference problems. German forward observers had the same frustrating experience as their American counterparts, radios that worked in training exercises but failed when they were needed most. The technical reasons were well understood by radio engineers. Amplitude modulation transmitted information by varying the strength of the radio wave. Any electrical interference, spark plugs firing, generators running, atmospheric static created additional amplitude variations that the receiver couldn't distinguish from the intended signal. The result was noise that drowned out the message. Military radios in 1942 faced a fundamental trade-off: range, reliability, or portability. Choose any two. High-powered radios with good range weren't portable. Portable radios had limited range, and nothing was truly reliable in the electromagnetic chaos of a modern battlefield. Artillery doctrine had adapted to these limitations. American artillery units planned fires based on the assumption that communication with forward observers would be intermittent at best. Pre-planned fire missions, registered concentrations, and time-on-target calculations all assumed that once the battle began, the observer might not be able to talk to the guns. Artillery would fire according to schedule, whether or not the observer could provide adjustments. This was profoundly wasteful. American artillery was learning to mass fires from multiple battalions, sometimes dozens of guns concentrating on a single target. But without reliable communication, that massed fire often fell on empty ground because the tactical situation had changed and the observer couldn't redirect it. More tragically, American infantry sometimes died under their own artillery fire because forward observers had no way to call check firing when friendly forces advanced faster than expected. By early 1942, this communication crisis had become what military planners called a critical deficiency. The U.S. Army was building the most powerful artillery force in the world, eventually fielding more guns than all other combatants combined, but those guns were deaf and blind without reliable communications. Several officers at the Signal Corps, engineering laboratories at Fort Monmouth, New Jersey, understood the problem with painful clarity. Major Roger Colton had written a memo in January 1942 arguing that American artillery would never reach its potential effectiveness until the communication problem was solved. Another officer, Major J.D. O'Connell, had gone further, arguing that the army needed to abandon its entire approach to tactical radios and start over with completely new technology. O'Connell's superiors thought he was being dramatic. After all, the army had contracts with several manufacturers to develop improved AM radios. Surely incremental improvements would eventually solve the problem, but O'Connell had seen something that made him certain incremental improvements wouldn't be enough. In October 1940, he'd been part of a delegation of Signal Corps officers who travelled to Hartford, Connecticut, to observe a demonstration of something called frequency modulation radio. The Connecticut State Police had a problem similar to the Army's. They needed reliable radio communication across the entire state, through valleys, over hills, in all weather conditions. Police cruisers needed to maintain contact with dispatchers while moving at high speed. The old AM police radios were inadequate. Static made messages unintelligible. Interference from vehicle engines created constant noise. Officers in rural areas lost contact with headquarters completely. Then the Connecticut police tried something different. They contracted with a professor of electrical engineering from the University of Connecticut named Daniel E. Noble, who convinced them to test a new type of radio system based on frequency modulation. FM radio worked on different physics than AM. Instead of varying the strength of the radio wave to encode information, FM varied the frequency the wave's pitch. In effect, the key advantage was that electrical interference affected signal strength, not frequency. An FM receiver could ignore amplitude variations entirely, filtering out the interference that made AM radios useless. The demonstration for the Signal Corps officers was remarkable. A police cruiser drove across Hartford, while the officer inside maintained a conversation with headquarters. The transmission remained clear, even when the cruiser passed under power lines, drove near industrial equipment, and navigated through areas that would have turned an AM radio signal into garbled noise. Major O'Connell asked the obvious question, "What's the range?" The answer stopped the conversation. With proper equipment, the Connecticut FM system could maintain clear voice communication at distances exceeding 25 miles. The Signal Corps officers looked at each other. 25 miles. With a vehicle-mounted radio, certainly, but still 25 miles of clear communication in a moving vehicle. If that capability could be adapted for military use, it would transform artillery, coordination. O'Connell pulled Noble aside after the demonstration. The professor was in his late 30s, with the slightly distracted air of someone who spent most of his time thinking about electromagnetic wave propagation. But when O'Connell started asking technical questions, Noble became intensely focused. "Could you make this portable?" O'Connell asked. "Something a soldier could carry on his back?" Noble considered. The components would need to be miniaturized. Battery consumption is an issue. FM transmitters need more power than comparable AM units. But theoretically, yes, it could be done. How long would it take? To design and build a working prototype? Perhaps a year. To move from prototype to production? Noble shrugged. That depends on how serious you are about this. O'Connell was very serious, but he wasn't the only one making decisions at the Signal Corps. Other officers remained skeptical of FM technology. It was unproven in military applications. The circuits were more complex than AM radios. The receivers required better components. Several manufacturers argued that improved AM radios would be cheaper and easier to produce. In early 1941, the Signal Corps let a contract for development of a new AM portable radio. The officer who secured that contract believed FM was a technological dead end. When Noble heard about it, he drove to Washington to meet with O'Connell, who had been promoted to colonel by then. The meeting was brief and blunt. "Colonel, that AM radio your people are developing is a mistake," Noble said. "It won't solve the interference problem. It won't give you the range you need. And it will fail soldiers in combat." O'Connell had heard this argument before. "Professor, I appreciate your conviction, but the AM contract is already, I can build you an FM radio that will work when AM radios fail," Noble interrupted. "Give me a contract and I'll prove it." The two men looked at each other. O'Connell was gambling. his career on the belief that FM technology was the answer to the Army's communication crisis. Noble was gambling his reputation on the belief that he could deliver what he promised. "All right," O'Connell finally said, "you'll get your contract, but you'll also get the toughest specifications we've ever written. If this radio fails in testing, FM is finished in this army. Understood?" Noble understood perfectly. Daniel Noble joined the Galvin Manufacturing Corporation, better known by its trade name Motorola, in September 1940. The company had already built a reputation for innovation in radio technology. They'd developed the first practical car radios in the 1930s. More recently, they'd built the SCR 536 handy-talkie for the Army, a compact AM radio that worked well enough for short-range squad communications. But what the Signal Corps wanted now was something far more ambitious. They wanted a portable FM transceiver combined transmitter receiver that could maintain clear voice communication at ranges exceeding 3 miles. It had to weigh less than 35 pounds with batteries. It had to operate for an entire day on those batteries. It had to withstand field conditions that destroyed laboratory equipment, and it had to be simple enough that soldiers with minimal technical training could operate it under combat stress. Oh, and the Army wanted it ready for combat deployment within 18 months. Noble assembled his engineering team carefully. Henryk Magnuski, a Polish-born radio frequency engineer, became the principal RF designer. Marion Bond handled circuit design. Lloyd Morris worked on power systems. Bill Vogel specialized in antenna theory and mechanical engineering. The Signal Corps gave them a designation before they'd built a single component, SCR 300. Signal Corps Radio, Model 300. The specifications were punishing. The radio had to operate in the 40 to 48 MHz frequency band, divided into 41 separate channels spaced 200 kHz apart. The transmitter needed to produce enough power to reach 3 miles minimum, 5 miles under ideal conditions. The receiver had to be sensitive enough to pick up weak signals, but robust enough to reject interference. Most critically, the radio had to include several features that had never been combined in a portable military radio before. Automatic frequency control would keep the transmitter and receiver locked to the same frequency without constant manual adjustment. Squelch circuits would silence the receiver when no signal was present, saving battery power and preventing operator fatigue from listening to constant noise. Waterproofing had to be sufficient for tropical deployment. The entire unit needed to survive rough handling that would destroy civilian radio equipment. The team worked through the winter of 1940 into 1941. Every component presented challenges. Vacuum. Tubes for the transmitter and receiver had to be selected for reliability and low power consumption. The frequency control oscillator needed only 2 crystals instead of the dozens required for comparable AM radios, a critical advantage given wartime shortages of high-quality quartz. The antenna had to be efficient across the entire operating range while remaining short enough for a soldier to carry through forest. By spring 1941, they had their first working prototype. It was crude, with exposed wiring and makeshift battery connections, but it transmitted and received FM signals according to specifications. The range in open terrain exceeded 5 miles. Interference from nearby vehicle engines barely affected signal quality. Noble drove the prototype to Fort Monmouth for informal testing. Signal Corps engineers subjected it to trials that would have destroyed most civilian radios. They ran it in hot sun and freezing rain. They operated it continuously until the batteries died. They dropped it, shook it, exposed it to dust and moisture. The radio kept working, but informal testing wasn't enough. The Signal Corps demanded formal acceptance trials under field conditions. The testing location would be Fort Knox, Kentucky, home of the Army's Armored Force School, and a proving ground notorious for destroying equipment that looked good in laboratories but failed in field use. The Fort Knox trials were scheduled for spring 1942. Noble's team had less than a year to transform their crude prototype into production-ready equipment. April 1942. Noble and his team had exactly 2 working SCR 300 radios suitable for demonstration. They'd been built, tested, disassembled, improved, and tested again countless times over the previous months. Every circuit had been optimized, every component had been proven. The radios worked beautifully in Chicago. Now they had to work in Kentucky, in front of the most skeptical audience the Army could assemble. The Infantry Board consisted of combat-experienced officers whose job was to evaluate new equipment and reject anything that wouldn't survive battlefield conditions. They'd rejected dozens of radio designs over the years. They had a well-earned reputation for being impossible to impress and quick to identify weaknesses that laboratory testing had missed. Bob Galvin, son of Motorola's founder, accompanied Noble and Bill Vogel to Fort Knox. The stakes couldn't have been higher. If these tests failed, the Army would cancel the FM program. More importantly, American soldiers would continue fighting with radios that failed them when they needed fire support most. The night before testing began, Noble and Vogel sat in their hotel room, performing final checks on both radios. Every tube, every connection, every battery contact received scrutiny. They couldn't afford a single malfunction. "The Infantry Board is going to try to break these," Vogel observed, running diagnostic tests for the dozenth time. Noble nodded. He'd read after-action reports from previous radio trials. The Infantry Board didn't just test equipment, they abused it deliberately. They'd driven tanks over radios, dropped them in streams, operated them in temperature extremes. One tester had reportedly thrown a radio off a second-story building just to see if the case would survive impact. "Let them try," Noble replied quietly. "We built these for infantry use, not laboratory use." But he still spent half the night double-checking every connection. The proving grounds at Fort Knox stretched across thousands of acres of Kentucky forest and rolling terrain. Colonel O'Connell had designed a comprehensive evaluation that would test the SCR-300 under conditions far more demanding than normal equipment trials. The first test was straightforward. Maximum range in open terrain. A radio operator with one SCR-300 would walk away from the command post in a straight line across open ground. Every quarter mile, he would stop and transmit a standard test message. Observers at the command post would track how far the signal remained intelligible. At 2 miles, the transmission was crystal clear. Infantry board officers exchanged glances. Existing backpack radios were already becoming scratchy at this distance, if they worked at all. At 3 miles, the Army's minimum specification, the signal remained perfectly clear. One colonel picked up the handset himself and spoke directly with the distant operator. No static, no fading, just clear voice communication that sounded like the operator was in the next room. At 4 miles, the signal quality remained strong. The infantry board officers were no longer exchanging glances. They were staring at the radio with the expression of men watching something that shouldn't be possible. At 5 miles in open terrain with good line of sight, the SCR-300 was still maintaining clear communications. The radio had exceeded its own design, specifications. But Noble knew the real test was coming. The second trial moved into Kentucky's wooded hill country terrain typical of what American forces would face in Europe or the Pacific. Hills blocked line-of-sight transmission, trees absorbed signal strength, valleys created dead zones where AM radios simply stopped functioning. The test operator disappeared into thick forest. After a mile, his voice came through the receiver. "Station 2, this is Station 1. Radio check. How do you read? Over." The reply was immediate. "Station 1, Station 2. Read you loud and clear. Over." At 2 miles through dense forest, the signal remained clear. At 2.5 miles, with a substantial ridge between transmitter and receiver, signal quality dropped noticeably, but the message remained completely intelligible. An AM radio would have been producing nothing but static at this point. Then came the interference trial the test Noble had been anticipating. They started a jeep next to the receiving station. In 1942, gasoline engine ignition systems were electromagnetic noise generators. Spark plugs created electrical interference with every firing cycle. Generators added their own noise. AM radios became nearly unusable near running engines. The SCR-300 receiver barely noticed. Signal quality remained unchanged. They started a second jeep, then a tank. The radio operator, 2.5 miles away, hidden behind a ridge in thick forest, continued transmitting clearly. His words cut through the electromagnetic chaos, as if the vehicles weren't running. An infantry board colonel picked up the handset and transmitted a message to the distant operator, received a clear response, turned to Noble with an expression that wasn't quite belief and wasn't quite skepticism. "Professor, this is impressive, but in actual combat, artillery batteries are typically positioned 8 to 12 miles behind the front lines, sometimes farther. Your radio won't reach that distance. How do you propose to solve that problem?" This was the question Noble had been waiting for. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The relay solution Noble walked to a map table and sketched out the tactical situation. "Colonel, the SCR-300 is designed for company and battalion level communications, forward observers talking to their fire direction centers within a few miles. But when you combine multiple radios using relay and rebroadcast techniques, the effective range extends dramatically." He drew the positions on the map. Imagine a forward observer with an SCR-300 positioned 3 miles ahead of his battalion command post. The battalion has a vehicle-mounted FM radio, say, an SCR-508 or SCR-608 with 10 to 15-mile range. The observer calls his fire mission to battalion. Battalion relays it to Division Artillery Headquarters 8 miles to the rear, also equipped with vehicle-mounted FM radios. Division Artillery coordinates fire from multiple battalions and transmits firing data directly to the gun batteries. Noble traced the communication path. Total distance from observer to guns, 11 miles, potentially more. But no single radio has to cover the entire span. Each link in the chain operates within its designed range. "That's not revolutionary," one officer objected. "We already use relay stations for long-distance wire communications." "True, but here's what makes FM different." Noble gestured to the equipment. "We can also implement direct rebroadcast. One SCR-300 receives the incoming signal and automatically retransmits it on the same frequency. We've built the connection points directly into the radio. Watch." The demonstration used 3 SCR-300 radios. Radio 1 remained at the command post. Radio 2 went 2 miles away. Radio 3 positioned itself 2 miles from Radio 2 in a different direction, 4 miles, total from Radio 1, well beyond normal communication range. Noble connected Radio 2 with a cable assembly, engaging the rebroadcast function. When Radio 1 transmitted, Radio 2 instantly received the signal and retransmitted it without any operator intervention. Radio 3, 4 miles from Radio 1, received the rebroadcast perfectly. 4 miles is just our demonstration distance, Noble explained. In actual field use, with proper positioning of portable and vehicle-mounted FM radios, you could establish communication networks across distances that were impossible with AM equipment. And because it's FM, interference from engines, artillery fire, or atmospheric conditions doesn't degrade the signal quality. The infantry board officers conferred quietly. Then Colonel O'Connell spoke. "Professor Noble, here's what we're going to do tomorrow. We're going to run a realistic artillery fire mission using your radio. Full forward observer procedures, actual artillery battalion, real guns. If the SCR-300 can handle that test, we'll know it's ready for combat." The next morning's test wasn't about radio specifications anymore. It was about demonstrating that FM technology could change how artillery worked on the modern battlefield. A forward observer team with an SCR-300 positioned themselves 3 miles from battalion headquarters in rough terrain that blocked line of sight. The battalion command post had an SCR-508 vehicle-mounted FM radio. 7 miles further back, an actual artillery battery stood ready with their guns laid and loaded. At 0800 hours precisely, the forward observer's voice came through the battalion radio. Fire mission, infantry in the open. Grid coordinates 473285. Request high explosive. Over. The Battalion Fire Direction Center received the mission clearly, calculated firing data accounting for range, elevation, wind, and propellant temperature. 7 seconds elapsed from the observer's initial call to the Fire Direction Center transmitting coordinates to the guns. The artillery battery fired. Shells arced across Kentucky morning sky. 30 seconds later, the forward observer reported impact. Splash. Right 200. Add 100. Over. The adjustment was transmitted to the guns. They fired again. The observer watched the impact, provided another correction. On the third salvo, he transmitted, fire for effect, target destroyed, end of mission. From initial call for fire to target destruction, 6 minutes. The entire fire mission had been coordinated faster than most artillery units could manage, with wire telephone connections half the distance. More importantly, the communications had remained clear throughout. No static, no fading, no missed transmissions requiring repetition. The forward observer had maintained continuous contact with his fire direction center, while German, or in this case, simulated German artillery fell around his position. Colonel O'Connell watched the demonstration with an expression Noble couldn't quite read. When the fire mission concluded, O'Connell turned to the assembled infantry board officers. Gentlemen, I believe we've seen enough. This equipment does exactly what we need. He looked at Noble. Professor, your radio works. More importantly, it changes what artillery can do on a modern battlefield. One of the infantry board colonels raised a hand. Colonel O'Connell, I want to understand the full capability. With relay positions and vehicle-mounted radios, what's the maximum distance a forward observer could effectively coordinate artillery fire? Noble did the mental calculation. SCR 300 to battalion, 3 to 5 miles. Battalion SCR 508 to division, 10 to 15 miles. Division could coordinate fires from batteries positioned another 5 to 8 miles further back. Total effective range from a single forward observer. He paused, making sure of the numbers. 15 to 20 miles, possibly more, with optimal relay positioning. The colonel wrote that down. So an infantry lieutenant with a backpack radio could call down fire from guns 15 miles away? Not directly, Noble clarified. But through the communication network? Yes, that's exactly what this system enables. The implications settled over the group. The U.S. Army was about to deploy an artillery coordination capability that no military force in history had ever possessed. The ability for frontline observers to mass fires from dozens of guns positioned miles beyond visual range, with real-time adjustment based on observed impact. Colonel O'Connell signed the acceptance documents that afternoon. Full-scale production of the SCR 300 was authorized immediately. Within 18 months, nearly 50,000 SCR 300 radios would be in the hands of American infantry and artillery units across every theater of war. The first SCR 300 radios reached American forces in North Africa in late 1942, but they arrived in small numbers, a few dozen units distributed to test their performance under actual combat conditions. The real deployment began with the invasion of Sicily in July 1943 and continued with the Italian mainland landings in September. Lieutenant James Corrigan received his first SCR 300 at a supply depot outside Naples in October 1943. He'd been serving as a forward observer with the 34th Infantry Division since the North Africa campaign, and he'd learned to hate the SCR 194 radio he'd been carrying. It failed constantly. It couldn't punch through interference. It had gotten men killed. When the supply sergeant handed him the new radio, Corrigan's first reaction was skepticism. He'd heard promises about improved equipment before, but Private Walsh, his radio operator, examined the SCR-300 with professional interest. "This is FM, Lieutenant," Walsh said, reading the technical plate. "Frequency modulation. I've heard about this. Supposed to cut right through interference." "Let's hope so," Corrigan replied, "because if it doesn't work any better than the last one, we're back to sending runners through machine gun fire." They tested the radio that evening, establishing contact with battalion headquarters 4 miles to the rear. The signal was so clear that Corrigan thought at first they must be using a vehicle-mounted radio at battalion. When he confirmed they were receiving his portable transmission, he looked at Walsh with new respect for the equipment. "Maybe this one's different," he said quietly. 3 days later, on that hillside above Salerno, Corrigan learned exactly how different it was. The German observation post he'd spotted was directing artillery fire on American positions. Taking it out was critical, but it was positioned on high ground that infantry couldn't assault without unacceptable casualties. Artillery could do the job, but only if Corrigan could call in the mission and adjust fire-based, on observed impacts. With the old radios, that would have been impossible at this range. In this terrain, with German shells falling close enough to shower them with stone chips from the wall they were hiding behind, with the SCR-300, it was almost easy. Fire mission. Enemy observation post. Grid coordinates. Corrigan read off the numbers, watched Walsh transmit them clearly to battalion. Within 60 seconds, the Fire Direction Center had calculated the firing data and transmitted it to the guns. The first salvo fell 200 yards short. Corrigan adjusted. Add 200, right 50. The second salvo landed close. He could see German soldiers scrambling away from the impact area. Drop 5 to 0. Fire for effect. The third salvo destroyed the observation post. The German artillery fire that had been falling on American positions ceased abruptly. Walsh was staring at the radio like it was a miracle. "Lieutenant, that was 8 minutes from initial call to target, destruction. And we're 3 miles from battalion. This thing just changed the war," Corrigan finished. "Walsh, every German position we can see, we can now kill. From anywhere." That realization was spreading through American forces across the Italian theater. Forward observers discovered they could coordinate artillery fire while moving with advancing infantry, something that had been nearly impossible with wire communications. Company commanders found they could call for fire support within minutes instead of hours. Artillery battalions learned they could mass fires from multiple batteries on targets identified by observers miles away. The system's full potential emerged when forward observers started using the relay and rebroadcast techniques that Noble's team had built into the radios. An observer with an SCR-300 could reach his battalion at 3 miles. Battalion could relay to division at 10 miles. Division could coordinate fires from artillery positioned another 8 miles back. The effective range of a single forward observer extended to distances that would have been impossible months earlier. One after-action report from the Battle for Monte Cassino described the impact. Forward observer maintained continuous contact with Fire Direction Center throughout 12-hour advance under heavy enemy fire. Coordinated artillery support from 3 separate battalions. Communications remained clear despite constant German counter-battery fire, our own supporting fires, and movement through difficult terrain. The SCR-300 radio performed flawlessly. Multiple enemy positions were destroyed that could not have been engaged with previous communication equipment. By early 1944, the transformation was visible in casualty statistics. American infantry units with SCR-300 equipped forward observers were suffering fewer casualties during attacks because they could call down suppressive fire on German positions before assaulting. German defenders reported that American artillery seemed to follow them everywhere the moment they revealed their positions. Shells would start falling with uncanny accuracy. What the Germans didn't understand was that American forward observers could now see enemy positions and instantly coordinate fires from guns the Germans didn't even know were in range. June 6, 1944. The beaches of Normandy. Thousands of American soldiers waded ashore that morning, carrying SCR-300 radios. The backpack units gave forward observers and company commanders a communication capability that hadn't existed in previous amphibious assaults. Immediate, reliable contact with artillery support, even in the chaos of an opposed landing. The impact was most dramatic in the airborne operations. Paratroopers from the 82nd and 101st Airborne Divisions, scattered across the Norman countryside in darkness, used SCR-300 radios to coordinate with artillery units landing with the amphibious forces hours later. Small groups of paratroopers, isolated behind German lines, could call down naval gunfire and artillery support on German counterattacks. On June 8th, forward observers from the 508th Parachute Infantry Regiment near Hill 30 were calling in artillery adjustments on German positions several miles away. The coordination happened so quickly that German forces attempting to reinforce their defences found themselves under accurate artillery fire within minutes of being spotted. One German officer, captured during the Normandy campaign, described the experience in interrogation. "We would identify an American position and prepare to attack. Before we could move, their artillery would begin falling on us. We could not understand how they knew where we were or how their guns could respond so quickly. It was as if they could see everything and strike anywhere." What the German officer was describing was the American artillery fire direction system operating at peak efficiency, enabled by FM radio communications. The system wasn't magic, it was mathematics, training, and technology working together. When a forward observer spotted a target, he transmitted grid coordinates to his fire direction center. The FDC calculated firing data for every gun within range of that target. Within seconds, dozens of artillery pieces could be firing coordinated salvos at a single point. If the first salvo missed, the observer provided immediate corrections. The guns adjusted and fired again. The speed was devastating. From target identification to shells landing rarely took more than 5 minutes. Often it was much faster. German forces had nothing comparable. Their artillery coordination relied primarily on telephone communications and pre-planned fire missions. They could mass fires effectively if given time to plan, but they couldn't respond rapidly to fleeting targets the way American artillery could. The British military historian John Keegan later wrote about American artillery effectiveness in Normandy. The Americans possessed a fire control system of remarkable sophistication. A single forward observer could bring down the fire of an entire artillery battalion, sometimes multiple battalions, on targets of opportunity. The system's responsiveness was unprecedented in military history. The psychological transformation. By late 1944, American infantry had developed a confidence in their artillery support that bordered on arrogance. They knew that if they could see an enemy position, they could destroy it. Distance didn't matter. Terrain didn't matter. As long as the forward observer had line of sight to the target and radio contact with his fire direction center, American artillery could reach it. This confidence changed how infantry fought. American units would fix German positions in place, then systematically destroy them with artillery rather than assault directly. Casualties dropped. Effectiveness increased. The infantry-artillery team became the dominant tactical system on the Western European battlefield. German soldiers learned to fear American artillery with an intensity that exceeded their fear of tanks or aircraft. Artillery was constant, accurate, and seemingly omnipresent. A German position that had been perfectly safe for hours could suddenly erupt in a storm of high explosive because an American observer spotted movement from 3 miles away. The psychological effect worked both ways. American forward observers, who had previously felt vulnerable and isolated, now felt powerful. They controlled devastating firepower from miles away. One lieutenant described it in a letter home. "I'm sitting on a hillside with a radio on my back, and I can reach out and touch the enemy from 5 miles away. It's like having the hand of God in my pocket." That sense of power came from technology, but the technology came from one engineer's refusal to accept conventional wisdom about what was possible. December 1944. The Ardennes Forest. When German forces launched their surprise offensive, they cut through American lines, isolated units, and severed telephone communications across a 100-mile front. In previous wars, such a breakthrough would have created communication chaos requiring days to restore. But American infantry companies and artillery battalions had SCR 300 and SCR 508 FM radios. Even when surrounded, forward observers maintained contact with fire support. Even when retreating, units coordinated artillery fire on pursuing German forces. The official U.S. Army history of the Battle of the Bulge specifically noted that the SCR 300 became key equipment that helped deter confusion during the German offensive. When wire communications failed, and they failed almost immediately, the FM radio network kept American artillery responsive and coordinated. One forward observer team, cut off from their battalion for 36 hours during the German advance, continued calling fire missions that disrupted German supply columns. They couldn't see their own forces. They didn't know if anyone was receiving their transmissions. But they kept broadcasting target coordinates, and somewhere to their rear, artillery batteries kept firing on those coordinates. When American forces finally relieved the isolated observer team, the lieutenant in charge learned that his fire missions had destroyed 2 German ammunition trucks, disabled a tank, and delayed a German regiment's advance by 6 hours. His SCR 300 had never stopped working. When the war in Europe ended in May 1945, the U.S. Army conducted an after-action analysis of communication equipment. The findings were stark. SCR 300 radios had a 92% operational readiness rate in field conditions. They worked in rain, snow, heat, and cold. They survived rough handling, accidental drops, and combat damage that would have destroyed more delicate equipment. Battery life exceeded specifications under normal use. A single battery charge could power the radio for 20 hours of receive time and several hours of transmit time. More importantly, the radios had fundamentally changed artillery effectiveness. American artillery units using FM radio coordination could mass fires faster, adjust more accurately, and respond more rapidly than any artillery force in the war. The numbers bore this out. American artillery expended more ammunition than any other combatant, not because they were wasteful, but because they could bring effective fire on more targets. A post-war study estimated that American artillery accounted for more than half of all German casualties on the Western Front. Some historians argued the percentage was even higher. The reason wasn't superior guns or better gunners. German and Soviet artillery was often excellent. The reason was superior fire direction and communication. The SCR 300 hadn't won the war by itself, but it had enabled a tactical system that gave American and Allied forces a decisive advantage in every engagement where artillery mattered, which was almost every engagement. Daniel Noble never claimed credit for winning battles. When he received the Army's Certificate of Merit for his role in developing the SCR 300, he deflected attention to his engineering team, Magnuski, Vogel, Morris, and Bond. The development of the walkie-talkie was an academic exercise, he said, compared to the contribution of the men on the battlefields fighting the war. But those men on the battlefields knew what the radio meant to them. It meant calling fire support when they needed it. It meant destroying enemy positions they couldn't assault. It meant survival. Lieutenant Corrigan and Private Walsh used their SCR 300 throughout the Italian campaign, into southern France, and finally into Germany itself. The radio Walsh carried in April 1943 was replaced several times, worn out from constant use, damaged in combat, or simply handed off to replacement operators when Walsh was promoted. But the capability remained constant. Clear communications, reliable coordination, artillery support when it mattered. In March 1945, Corrigan found himself on a hillside overlooking the Rhine River, watching German positions on the far bank. He had a new radio operator. Walsh had been rotated home after earning a battlefield commission, but the same SCR 300 radio he'd learned to trust 18 months earlier. "Lieutenant, we've got a clear view of those bunkers," the new operator said. "Want me to call it in?" Corrigan looked at the German positions, calculating distances and angles. 4 miles to battalion, another 9 miles to the division artillery that would fire the mission. Total distance, 13 miles from where he stood to the guns that would fire. 2 years earlier, coordinating this fire mission would have been impossible. Wire communications couldn't span that distance in combat conditions. AM radios wouldn't have worked. Corrigan would have been reduced to sending a runner or abandoning the mission entirely. Now it was routine. "Call it in," Corrigan ordered. "Let's see if we can ruin their morning." The operator transmitted. Battalion received. Division artillery calculated. Guns fired. 3 minutes from target identification to shells landing. The German bunkers disappeared in a storm of high explosive. Corrigan watched the impact and thought about Professor Noble in his laboratory in Chicago, working late into the night to solve a problem that everyone said couldn't be solved. Noble had given American infantry a gift that was difficult to quantify, but impossible to overstate. The ability to reach out across distances that had previously meant isolation and death, and bring down the thunder. The SCR-300 remained in service long after World War II ended. American forces used them in Korea. The basic design influenced military radio development for decades. But the radio's true legacy wasn't technological, it was tactical. Noble's FM radio proved that conventional wisdom was often wrong. Every radio engineer in 1942 knew that you couldn't build a portable radio that was powerful, reliable, and long-ranged. Noble built exactly that by refusing to accept the constraints of existing technology. The relay and rebroadcast techniques that Noble's team built into the SCR-300 demonstrated another principle. You don't need one perfect solution if you can network multiple good solutions. A forward observer didn't need a radio that could reach 15 miles. He needed a radio that could reach 3 miles, connected to a system that could relay his message to guns 15 miles away. That principle, distributed networking instead of centralized power, would eventually transform all military communications. But in 1943, it was revolutionary. The title asked how one engineer's crazy frequency trick let infantry call fire 15 miles away. The answer wasn't a single trick. It was FM technology that rejected interference, automatic frequency control that simplified operation, relay techniques that extended range, and a fire direction system that could coordinate fires from multiple batteries. But behind all the technology was a more fundamental answer. One engineer believed the problem could be solved, assembled a team, and worked until they solved it. Daniel Noble didn't accept that portable, powerful, and reliable were mutually exclusive. He built a radio that was all three. And because he did, thousands of soldiers who would have died without artillery support came home alive. That April morning in 1943, when Lieutenant Corrigan watched German positions disappear under artillery fire called from 3 miles away, he didn't know Professor Noble's name. He didn't understand the physics of frequency modulation. He didn't care about automatic frequency control or squelch circuits. He just knew that the radio worked when he needed it, and in combat, that was everything. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.